Today we're gonna talk about this SN2 reaction. What are they? And then what's the mechanism for SN2 reactions, and what is the kinetic evidence supporting the mechanism of SN2 reaction, and what kind of stereochemical evidence we have in order to confirm the proposed mechanism for SN2 reaction. And before we start specifically talking about SN2 reaction, we have to talk about substitution in general and presence of two possible mechanisms for this specific reaction. First one is concerted mechanism that we can propose, where nucleophile attacks and leaving group leaves. And by the way, definition of concerted, we have introduced it in the previous session, where concerted reaction is one step and that processes in that step happen simultaneously. So basically concerted means simultaneous, at the same time, synchronous. On the other hand, stepwise reaction goes through the formation of reactive intermediates, and these reactive intermediates could be radicals, carbocations, or carboanions. So first possible mechanism that could be proposed for any substitution reaction is concerted mechanism, where nucleophile attacks at the same time leaving group goes. The second mechanism, type of the mechanism that we can propose, is stepwise mechanism, and here leaving group goes first and then nucleophile attack next. So as you can see, both of these mechanisms share the same step, nucleophilic attack and the loss of leaving group, but timing differs. In the first concerted mechanism that's proposed, nucleophile attack and leaving group leaving happens at the same time, synchronously, simultaneously. But in stepwise mechanism, we give some time for leaving group to leave first and then nucleophile attacks. And now we're going to learn these mechanisms and how they are supported kinetically and stereochemically for SN2 reaction and then for SN1 reaction. So SN2 is concerted mechanism and SN1 is a stepwise mechanism. But before we move on to details, we have to talk about why we have to learn mechanisms, why mechanism matters. So I will show this by using this alcohol as an example. If you look at commonly used nucleophilic substitution, the replacement of OH by bromine, we will find out that two different reaction conditions are used depending on the structure of the alcohol. Here, this is tertiary alcohol because this is alpha position that's directly connected to OH, and we have 3 beta positions, so we call this tertiary. But here, there is only one beta position, so we call this as primary alcohol, just like halides as well. Tertiary halides, primary halides, secondary halides, and so on. So what happens here is that when it is tertiary alcohol, I am just using hydrogen bromide as my reagent in order to perform this transformation. But when I use primary alcohol, I have to use another reagent. So the main point here is that if we know which mechanism a compound reacts by, we know what sort of conditions we have to employ in order to get high results, not just in substitution, but in any reaction. Because otherwise we have to conduct some kind of kinetic experiments. For example, this is just oxygen nucleophiles and then their performance in SN2 reactions. And as you can see, there is some kind of trend when you go from OH to H2O and then your rate decreases. Or we can use kinetic experiments in order to confirm leaving group ability of halides. And when you go from fluorine to iodine, the rate of reaction also increases. So that means iodine is much better. So if I want to perform substitution reaction, I'm going to choose obviously iodide as a leaving group. So I will have to choose alkyl halide with iodide as halide. And oxygen nucleophile, I'm probably going to choose OH minus because it's the fastest. But rather than doing kinetic experiments to find out, it's important to be able to predict which mechanism is likely to apply to any reaction. So I have a reaction, I have to know the mechanism. So based on mechanism, I will know naturally what kind of substrates, what kind of nucleophiles, what kind of electrophiles are better suited for that specific mechanism so that I can make informed decisions about what kind of reagents, what kind of conditions I can employ so that I can get the best yields out of the reaction. So that's the reason why we are learning mechanisms. So let's go back to SN2 reaction, and one of the most important tools we use in order to find out the mechanism for any reaction is actually to conduct kinetic studies. And conducting kinetic studies for substitution reaction, for specifically SN2 type substitution reaction, we find out that the reaction rate depends on both halide and nucleophile. this is supported by kinetic studies. So we say kinetic evidence suggests that reaction rate depends on both halide and nucleophile. And this is just one example where methyl sulfide is used as a nucleophile and we have methyl iodide as a substrate, alkyl halide. And this could be SN2 reaction. We don't know yet, right? And what we do is we perform this kind of experiment while keeping the concentration of nucleophile constant. We are increasing the concentration of alkyl halide and we see that the rate also increases. For example, when we double the concentration of methyl iodide, the rate also doubles. And in the next experiment, we'll keep the concentration of methyl iodide constant and we do the same for nucleophile and we still find the same trend that doubling the concentration of nucleophile doubles the reaction rate. And from that, we see that this is second order process. Reaction is first order with respect to alkyl halide and it's also first order with respect to nucleophile. And as you remember, kinetic order of the reaction, kinetic order is actually sum of the orders with respect to reactant I, and this I is just from 0 to n. So for each reactant, we find the order and we sum those order up. So here, my first reactant is alkyl halide and it's first order, and it's also first order with respect to nucleophile, and then I add them up, it gives me second order. So the kinetic order of this reaction is 2, basically, so we call the second order reaction, and that actually gives the name for SN2. So 2 here is bimolecular. So that means the rate of the reaction depends on the concentration of both alkyl halide and nucleophile. So that's why we put 2, and N here means nucleophilic substitution, and S is obviously substitution because we also can have electrophilic aromatic substitution, for example. In that case, it's E. N specifically suggests that this is nucleophilic substitution. So this is the kinetic evidence. So the conclusion here is that the experimental observations for SN2 reactions are consistent with a concerted process involving both the nucleophile and alkyl halide in a single step. And this is the accepted mechanism for SN2 reaction. Nucleophile attacks and carbon halide bond breaks, and then that the bond between carbon and halide breaks and the electrons on the bond are landed onto leaving group. That's why it becomes negative. So we introduce SN2 reaction, we introduce the mechanism, and then we also talk about the kinetic studies, the kinetic evidence that supports this concerted process. But there's also stereochemical evidence that supports this concerted process. And this is another crucial piece of evidence. And this is specific in a sense that when we have a chiral center in alpha position, we observe a change in configuration. So this is just one example, bromide, and then we use sulfate as nucleophile, and it is originally R, and now in the product it is S. So we call this change in configuration as inversion of configuration, also called Walden inversion, the chemist who discovered this inversion. So in order to understand this, let's just zoom in this substrate, and we see that there are actually two phases, two possibilities for nucleophile to attack. First is called front attack, second is back attack. Front attack means that we are attacking from the same side as the leaving group leaves, and back attack means we are attacking from the opposite side to the leaving group. And the rule says that nucleophile can only attack from the back side, never from the front side. That's the reasoning behind the configuration. So our nucleophile comes and it's going to replace the bromine, but it does not come from the front, it comes from the back. So that's why we are having this inversion of configuration. So what is the reason behind this preference for back attack and basically impossibility of front attack? In order to understand that, we have to explore the transition state. We already can guess the transition state is that we have a pentavalent carbon temporarily. We have a bond that's being formed between incoming nucleophile and the carbon. And we also have a bond breaking between carbon and leaving group. And as you know, we always show transition state with square brackets with double dagger symbol. So this is the transition state for SN2 reaction. And the reason why we are having back attack instead of front attack is because this bromine leaving has high electron density here. And this incoming nucleophile should come from the opposite side. so that we don't have a crowded negative charge. Or in another picture, you can see it like this. We have a transition state. Carbon is forming a bond with nucleophile, breaking a bond with a leaving group. And both of these, the incoming nucleophile and leaving group, are just shown with red color in electrostatic map. This is electrostatic map where colors are corresponding to electron density. So the red color means electron rich, electron dense regions. Green means neutral, blue means electropositive regions. So as you can see, we have partial negative charge on both sides of transition state. But if we try to put, let's say we are having front attack, what's going to happen is carbon breaking bond with bromine and also forming a bond with nucleophile, but then they are on the same side. We have two sides with very high electron density just next to each other, which is going to immensely increase the energy of transition state. So that's the reason why we never allow for front attack. So basically what happens here is that observed stereochemical outcome here is the inversion of configuration. We had R in the beginning and then now it is S. So this is consistent with concerted mechanism. Nucleophile attacks with simultaneous loss of leaving group. Because if we had otherwise, leaving group leaves first and then nucleophile attacks later, we wouldn't have this kind of transition state. We wouldn't have a need for back attack only, right? So that's another crucial piece of evidence that supports the concerted mechanism that we have proposed. And here, the chiral center behaves like an umbrella flipping in the wind. So if you see this is some kind of umbrella like this, but now after nucleophile attack, it flipped around. So you can also remember this inversion like that. And another important thing I would like to mention here is that this flipping is much more important than R becoming S, because that's not always the case. We don't have to learn in a way that, oh, it's R in the reactants, and now after SN2 reaction, it's going to become S. No, because R and S are absolute configuration. They are the ones that we assign, and they are based on the priority of the groups. If my incoming nucleophile has lower priority than other groups, then it might as well stay as R. So it was R in the beginning, and it could be R. So it doesn't necessarily mean that I have to change the configuration. So please be careful here. It's just that you are changing the 3D spatial arrangement, and then you assign the configuration. And in most cases, it changes from R to S or S to R, but that's not always the case. Because the reason why we are usually writing that R is becoming S and S is becoming R is because incoming nucleophile usually have the highest priority as the leaving group. So I have my original reactants where let's say 3 something on the front, on the back. So let's say I have some original alkyl halide with some alkyl groups, and then this is my leaving group on the plane. And this is usually the first priority, and this is, let's say, 2, and this is 3, right? And then this becomes nucleophile, but other things are kept intact. So this is still 2, this is 4, you don't need to show 4, and this is 3, right? And wait, and this is 3. And nucleophile usually has 1. So what happens here is that priority 1. So what happens here is that I had counterclockwise before, and now I have clockwise. And see, and as you can see, group number 4 is on the back, so counterclockwise is gonna be S, and in this specific example, and clockwise is gonna be R. So you see, I changed from S to R because usually my leaving group and nucleophile are prioritized as 1. But there could be cases where I will show the same example, but this time we don't have nucleophile or leaving group as number 1. Or maybe leaving group is number 1, but nucleophile is no longer number 1. So let's see. I have still an alkyl halide where my alkyl group is priority number 1. Let's say this is 2, and the one in the plane is 3. And nucleophile attacks and leaving group leaves, and it's back attack. Nothing changed the fact that it's gonna be back attack. Assume that nucleophile here does not have first priority, so it's lower than the second. So let's assume that this is type of a nucleophile that has a lower priority, and instead of putting nucleophile as first, now this is gonna be the first. So nucleophile has priority 2, and this group has still 3. So basically, incoming nucleophile is no longer 1, but this is higher priority. So this group number 2, whatever it was that, it was number 2 in terms of priority in the reactants because it was lower than the leaving group. But now it's higher than the nucleophile because it depends on the identity of nucleophile, right? And now in the reactants, we have counterclockwise. And since the group number 4 is on the back, counterclockwise is S. But here I have, again, counterclockwise, and it is still S. So I am still having S both in the reactants and in the products, but it's still back attack. Nucleophile came from the opposite side to the outgoing leaving group, right? So I still have back attack. It is still called inversion of configuration because it is inverted, but just due to nucleophile being lower priority, this did not change the configuration necessarily because the RNAs are absolute configuration and that depends on the identity of the groups, priority of the groups. Now let's solve this problem. It says R2-bromobutane is treated with sodium hydroxide. Mixture of the product is obtained. One of the minor products is generated by SN2 reaction and another is elimination, which we'll discuss later. So they ask us to draw SN2 product that's obtained from R2-bromobutane. So what we need to do first, we have to draw the structure. They are all names. We have to convert them into structure. So basically the question asks reaction of R2-bromobutane with hydroxide. So hydroxide is just OH minus. We don't need to show this counter ion, sodium plus. They do not participate in the reaction mechanism. And here we have 2-bromobutane. So 1, 2, 3, 4. And in the second, I have 2-bromo. And it's R. Let's just try to find out. So the number I put here is the IUPAC numbering, but now I'm going to put Chan-Ingold Prelog priority numbers. So bromine is the first, this is second, this is third, and hydrogen is on the back. So this is clockwise, the smallest group is on the back, it's going to be R. And what's going to happen is that OH is going to attack and replace bromine according to SN2 mechanism. And I'm going to have OH. But then as you can see, this OH group is on the back because this bromine is coming towards us. And this OH is going to attack from the back. Basically, if you just see this screen as 2D dimensional plane, the bromine here is making a hole and it's coming towards us. And this OH is going to come from the behind the screen. So that's the definition of back attack. And that's the reason why in the resultant product, OH is attached to the carbon from the backside.